So I actually, before we go into reading, I feel like we should at least discuss what was left before we go into reading. And we still got some parts of the batch norm unfinished. So let's do that. Okay, so I believe we kind of did what was here. And I think this is where we left off, so we'll finish this. And before we go into reading on gradient clipping quickly. So, okay. So let me just start reading. And this is an important paragraph. Batch normalization does, however, add some complexity to the model. Moreover, there is runtime penalty. The neural network makes slower predictions due to the extra computations required at each layer. Fortunately, it is often possible to fuse the BN layer with the previous layer. After training, thereby avoiding the runtime penalty, this is done by updating the previous layer's weights and biases so that it directly produces outputs of the appropriate scale and offset. For example, if the previous layer computes x times w plus b, then the bn layer would compute gamma element-wise multiplication parenthesis xw plus b minus mu divided by sigma plus beta. So what does it mean? It's basically, if you look at this, it's basically this, right? But instead of x, you put in the xw plus b. So that's your x, right? That's the output of the linear layer. Then you output that. Then you element-wise multiply with gamma, the scale parameter gamma, then plus the beta parameter, which is the shift parameter. Okay. So ignoring the smoothing term epsilon in the denominator, if we define w equals to gamma element-wise multiply w divided by sigma, and b equals to gamma element-wise multiply b minus mu divided by sigma plus beta, the equation simplifies to xw plus b. So let me just so if we replace the previous layer's weights and biases, w and b, with the updated weights and biases, we can get rid of the bn layer. TF Lite's converter does this automatically. So note, you may find that training is rather slow because each epoch takes much more time when you use batch normalization. This is usually counterbalanced by the fact that convergence is much faster with BN. So we'll take fewer epochs to reach the same performance. All in all, wall time will usually be shorter. This is the time measured by the clock on your wall. Okay, any questions, any comments on this?
So if you go back up and look at the equations again, just scrolling back up there, scrolling up farther to where they have the three equations. Oh, there it is. Yeah. So if you look at, equation 1 is calculating a mean, equation 2 is calculating a variance, and then what's equation 3 doing? If you ignore the epsilon, which is just to make sure that it doesn't blow up when the variance is small, what is that doing? That looks to me like standardization, right?
Right, exactly.
So it's standardizing, but then it's doing something else. It's saying, okay, let's give you a chance to sort of super standardize. We're going to give you we're going to give the network a chance to calculate a new parameter gamma and a new scaling parameter gamma, and a new offset parameter beta that will help that will make the standardization even better for getting a high score in the end, right? So you're actually the gamma and the beta are actually being learned, and so that's what this batch normalization is doing. It's sort of making standardization happen every batch, and but it's also giving you a chance to make the standardization even better by having the extra scaling and offset parameter that get tuned by the network.
Correct. Yes. Yes, and we'll go into a little more detail when we flip the page. Actually, when we flip 2 pages, it will go into a little more detail in terms of mathematics and how the shapes get determined and how this evaluation is done over the mini batch. So let's keep reading. And thank you, Joseph. Okay. So, okay, here we are. Okay, so then basically we just use batch normalization, you know, as I kind of previously pointed out before the end of the session on the first session of this chapter. It's quite intuitive, and you just pretty much put it, you know, after each linear layer, and for the first layer, it's input layer, just added in as well. So it's just calling the keras.layers.batch normalization. As keras, you know, it's very intuitive and straightforward and simple as well. And it abstracts most of the code away for people already. Okay, so just add a batch normalization layer before or after each hidden layer's activation function, and optionally add a BN layer as well as the first layer in your model. For example, this model applies BN after every hidden layer, N as the first layer in the model after flattening the input images. Okay, that's all. And when you call model.summary, you know, basically this is none, this is 784, so you know, it was previously 28 by 28, now it's flattened to be 1 by 784, and of course if you set up the batch size, then it will be like, you know, batch size 784, and obviously there's no training parameters here, and 784. So batch normalization is element-wise, and so it doesn't change the shape. It doesn't alter the shape. It keeps the shape the same. And then you have a dense layer of 300 neurons. And when we say neurons, it just means 300 columns. And the other the other dimension is already determined when you do the matrix multiplication, right? So you just have to determine the number of hidden units, or 300 right here, and then you get this is the number of parameters that are trainable. Well, number of parameters period. And this is number of parameters with the batch normalization, and it will go through a little bit on the calculation wise, and the total parameters is 271,000, trainable parameters 268, and non-trainable 2368. And the way how you get that 2368 is you literally add up all the BN layers parameters, which is 3,136 plus 1,200 plus 400, and divided by 2. Why divided by 2? Because out of that 4 parameters in each BN layer, only gamma and beta are trainable. Mu and sigma are estimated, so they're not necessarily trainable. And so you divide it by 2, and so that's your 2360A. And if you add them up, that's your two total parameters. And also you can see that, basically by var.name, var.trainable for var in model.layers, one variables. And so if this is layer 0, then this is layer 1, and layer 1 is a batch norm layer. And you can call the variables, then you get that as a tuple. And is a trainable true, true, false, false. So gamma and beta are trainable. The moving mean and moving variance are not, so they're false. Okay, and it also creates two operations. Now, when you create a BN layer in Keras, it also creates two operations that will be called by Keras at each iteration during training. These operations will update the moving averages since we're using the TensorFlow backend. Okay, so, and the authors of BN paper argued in favor of adding the BN layers before the activation function. And we mentioned a little bit on that as well towards the end of the last session. There is some debate about this, which is preferable seems to depend on the task. You can experiment with this too to see which option works best on your data sets. To add the BN layers before the activation functions, you must remove the activation function from the hidden layers and add them as separate layers after the BN layers. Moreover, since a batch normalization layer includes one offset parameter per input, you can remove the bias term from the previous layer. Okay, so here's how it's laid out and structured. Basically, just put it in right here, and so you actually don't, you set this as false because a batch normalization includes one offset parameter per input. So you don't even use bias here. Okay, so then he also used elu instead of relu. And in the end, you have a dense layer of class of 10 with an activation of softmax. And that's your output layer. Okay, any questions, comments?
Yeah, just a comment. It's I guess they're still arguing about whether to use batch norm before or after the activations. But to me, it seems it seems more logical. I mean, it just seems more reasonable to do the batch normalization after the activation, because that way the input at every point will be standardized. In other words, it'll have that it'll have its norm, its standard deviation, and it's brought back to 1, and its mean brought back to 0 in place before at the input to every next layer. You know what I'm saying? So that's why it seems to me more reasonable to do the batch normalization after the activation. Because if you do it before the activation, then then everything is standardized before the activation, but then the activation maps it somewhere else. Maps everything somewhere else, and so you've sort of screwed it up. So it just seems to me more reasonable to do the batch normalization after the activation.
I wonder how much difference in terms of performance it can make, and just by switching the order of these two layers.
Yeah, that'd be a good experiment to do. But apparently, people have found that sometimes it works better to do the batch normalization before the activation, and sometimes it works better to do after. So the jury's not in on that. I think you just have to view that as a hyperparameter in some sense.
So we got 86%. Why don't we do it now? So okay, so we got batch norm, dense activation, batch norm, dense activation, batch norm, output layer. Great. So In the end, after 10 epochs, we previously had 86% on validation accuracy. So let's see that now. Okay, while it's running, let's keep reading. Okay. So momentum. And the batch normalization class has quite a few hyperparameters you can tweak. The defaults will usually be fine, but you may occasionally need to tweak the momentum. This hyperparameter is used by the batch normalization layer when it updates the exponential moving averages. Giving a new value, v, a new vector of input means or standard deviations computed over the current batch, the layer updates the running average v using the following equation. V times v vector times momentum plus v times 1 minus momentum. And momentum is just 0.9 or 0.99 or 0.999. And it's basically, you know, the previous vector of the running average. Basically a new value you times that, and the running average you times this 0.9. So that you kind of you slow down the process a little bit. So let's see. Oh, I actually have a higher accuracy. Okay, well, that's surprising. So I guess, you know, it's not so much different. 86.6 versus 87.2 is 0.6% difference. But hey, it is higher. Okay. We just experimented that quickly. Okay, sorry, back to this. And yes, so basically a go momentum value is typically close to 1. So, you know, 0.9, 0.99, or 0.999. You want more 9s for larger data sets and smaller mini batches. Okay, that's a good rule of thumb to remember. Another important hyperparameter is axis. And this is where we get to a little bit of calculation. And when I was reading it, I was a little confused as well in terms of how this mean and standard deviation are calculated dimensionally. So let's read about it and let's see how it's actually calculated. Another important hyperparameter is axis. It determines which axis should be normalized. It defaults to -1, meaning that by default, it would normalize the last axis using the means and standard deviations computed across the other axis. When the input batch is 2D, the batch shape is batch size features. This means that each input feature will be normalized based on the mean and standard deviation computed across all the instances in the batch. For example, if the first BN layer in the previous code example will independently normalize each of the 784 input features. And let's stop here, because I thought, you know, when I was reading it, I thought this was done on a vector basis, but then he was saying this was done independently of each of the 784 input features. When I was reading the equation, I literally thought this was a vector, and if the batch size is 64, you literally have 64 vectors, sum them up, divided by 64, then you get your mu bay.
That's actually what's happening. I mean, if you think of xi as the you know, the vector of all the pixels for that batch, okay?
Yeah.
And then you sum them, and you sum each pixel. So xi is a vector of length 784, right?
Right.
And when you take the sum, you're basically summing up you're not summing the vector to get 1. You're summing up 32. If the batch size is 32, you're summing up 32 of those vectors and taking the mean.
Right.
Right? And that means that each pixel is being normalized independently, because, you know, the first element in that vector is the first pixel, right? And so what's the sum doing? It's adding up over the entire batch all the values for that first pixel, and then dividing it by the number in the batch.
Right.
So every pixel is being normalized independently in that equation. It's just, yeah.
Okay, it's just done in a vector, right? And similarly, you know, this is a vector minus your main vector, and so for, like, you know, however many vectors you have in a batch, or however many, you know, instances you have in a batch, then you do this, then you sum the square sum, then you divide it by, you know, the batch size, get your standard deviation. Then this is your kind of the standardized vector. Then you times a parameter that's called gamma element-wise. Now, is gamma a scalar?
Yeah, it should be a scalar.
It should be a scalar. Okay, then you times that element-wise, and plus beta. Is beta also a scalar?
Yeah, yeah.
Okay, then
I think so.
then you
May I ask a question here?
Yeah.
So what's the intuition going from 3 to 4? So we're taking the standardized X estimate in 3, and then we multiply it by that scalar gamma. What is the intuition going from 3 to 4, where now you take that estimate in 3 and you scale it with the scalar gamma plus, of course, the shift parameter?
Right.
Beta.
So what that's doing is it's saying, all right, you've standardized, but now let's give you a chance to make that more flexible. So now we're going to say, all right, give us a scale parameter and an offset parameter that you fit from the network, and train those parameters to make the standardization even better. Because that's what training gamma and beta means. It means finding the right values that's going to tweak the score higher. So you're sort of making the normalization a little more flexible, giving it some extra, by giving it those 2 extra parameters.
How do you pick the values of gamma then? How do you pick the value of gamma?
You pick them, as I said, you pick the value of gamma and beta that make the score that minimize the loss function, that lead to a smaller loss function, right? Because
It's
they're
trained.
being.
It's not picked.
Pardon?
It's trained, not picked.
That's what I'm talking about. The training picks the values of gamma and beta that minimize the loss function. So the network learns those parameters. The network learns those parameters. Yes.
Got it.
I've also seen it referred to as allowing the, increasing or allowing an increase in the expressiveness of the network. So in that sense, you're no longer limited by the mean and the standard deviation. The network learns, as part of the feedback it gets from the loss and stuff, what gamma and beta should be in order to match the output better to what values it sees as it gets supervised.
Very good.
So it allows the network, I've seen words to the effect that it expands on the expressiveness of the network, which means basically that it allows the network, as Joseph was explaining, to get closer to the output values that it sees and not limited by the mean and the standard deviation of the batches.
Love that description. Allows the expressiveness of the network to capture the exact values.
Right.
So you can ask yourself, what is it doing? Is it increasing or decreasing the bias, or increasing or decreasing the variance?
The variance.
So it's making the variance smaller. It's making this model more flexible.
Gamma and beta should be vectors, right? They'll be vectors of the size of the batch.
Yeah, I think you're right. Yeah, you're right. I misspoke before.
Sorry, so is that a scalar or a vector?
No, it's a vector.
It's a vector.
It's a vector of D dimension.
Yes.
Yeah,
it actually says right here. So scale parameter vector. So it is a vector, and it should match the dimension of this, right?
Yeah.
Okay.
That's why they're doing dot product with the input.
Well, no, this is not a dot product operation. This is element-wise.
Oh, sorry, element
multiplication. Yeah. So you literally,
We should look at that formula for this for the variance in part 2, because the variance is also, it turns out it's going to be a vector, and but when you look at that formula, if you look at it if you look at it, it looks like a scalar so what it must be going on there is that squaring must be an element by element squaring. The xi minus mu b squared, that must be element by element, because that's the only way that
Yeah.
the variance can be a vector.
Okay, so
gamma and xi are not the same size, Wenchang.
say it again.
Gamma and xi I think that's what you were pointing to, they are not of the same size. Gamma should be a vector which should be the length of how big your batch is. So in this case, if you're using a batch of 32, gamma will be for each sample, you'll have one gamma value. Whereas xi is determined by what the shape of your image is, which is 784. And the element wise is just saying that you take gamma 0 for the first image and multiply it through all the 784 elements in that.
Huh.
No, gamma should be as large as your input, Rakil.
Should be as large as your input.
It's not
meaning
dependent
the
on
size
it says contains one scale parameter per input. What does that mean?
Exactly. So that's what. So if you have 32 images in your batch, you'll have 32 gamma values. But that doesn't mean that your input is 32, right? Your input is 784.
Somebody's dropping out. I can't hear.
Sorry, Gautam, can't hear you. Can you repeat again?
Gotham, you here? We can't hear you. Okay, well, okay. Yeah, sorry, Gotham, we couldn't hear you. You might want to reconnect or something so we can hear you better. Okay. Rekil, sorry, what were you saying?
I just wanted to kind of clarify that gamma is a vector which should be as long as your batch size. So will beta be. This holds for both gamma and beta according to my understanding. So if your batch size is 32, that means you're using 32 images, let's say. Each will have a gamma and a beta.
Got it. Each row will have one gamma.
Yeah, in this case, yes, because you're flattening the image down into 784. Yes.
Yeah.
In that sense, yeah, each row will have.
Got it.
I think the language could be made clearer in this page, because they talk about instance I and they talk about input, and I think they both mean the same thing. So an instance is the same as an example or a sample, or and when they say input, and when they say input, they also mean an example or a sample.
Instance is a row.
It's one 784 vector. In other words, it's one it's one image, right?
Right, one image.
So input, instance, example, sample, these are all the same thing, and it would be helpful if they tightened up the language there so that it would be more clear.
Right, that's why it's a little confusing. Okay, so let's go back to what he was saying back here. He was saying when it's batch size by features, this means each input feature will be normalized based on the mean and standard deviation computed across all the instances in batch. So that means each row will be normalized, and that's what we saw, I guess. For example, the first PN layer in the previous code example, we independently normalized each of the 784 input features. Now then 784 input feature is 1 pixel, so
hang on one second, Wenchang. I think for clarity in language, if you try to arrange this up as 784 rows and you stack up 32 images like that, right? So at the end of the day, when you kind of get back your scale stuff, when you're first calculating your mean and your variance, you'll still get back a vector which is 784 long, right? Because you're calculating the mean and variance for these 784 input features down each column, which is basically across each image.
Okay. So
it's not, you're doing it across 784. That's not the way. It should be each feature of these 784 things down the 32, which is the batch size.
Each pixel in this case is each column, as Raquel refers to, and it's better to think of it that way. It's the 784 pixels are arranged in 784 columns, and then there are 32 such entities, and you average across the per column.
Then it's 784 columns.
Yes, your mean and your variance will be that size. Your mu b and your mu b.
Then why do we have MB here?
That's just the average. That's just to
right?
that's just averaging over the number of batches, number of elements in the batch.
So that's 32, for example.
Yeah.
So we're divided by 32 here, but you're saying it's so
because you're stacking 32 images one over the other, right?
Right.
So you're trying to take the mean of that. So imagine this: if you have 784 by 1 is basically one image, right? So if I give you 32 images, you'll have 784 by 32, right?
Right.
And now I tell you calculate the mean. You're not calculating the mean for each image. It's the mean for each feature, and each feature is 784, one of the 784 in the dimension. So now you're calculating the mean for each of these 32 images that are there, but one feature at a time, 0 to 784.
Okay. Okay, I didn't read that from, I guess I didn't read that from here.
Yeah, the notation is kind of, with the bold and eyes and all that stuff.
Okay.
That's what is happening from what I have understood. That's why mu b and mu b square will be the same size as that input vector that you're kind of getting your image size, right? 784 sort of a thing.
Yeah, and another plug for this tensor sensor thing that the guy who wrote with Jeremy, the math thing, because if you apply that, which shows the shape of the matrices, then you'll figure, or we'll be able to figure how each of these steps is happening and what the shapes are.
And then if you look at the last number 4 to try to make sense out of that, okay, so x bar I, x hat I is 32 by 784, right? It's a matrix, and we're going to multiply gamma by it. Gamma is a 32 is a vector, a column vector of length 32. So that first term is basically broadcasting that 32 column vector times the matrix, and so it's going to multiply that column vector gamma times every column in the matrix, column by column, and then
that be when you say column, is the column the image over here?
The column is the the column is just as you said. Each column, each pixel corresponds to a column. So xi is 32 by 784 is a matrix, right?
Right.
For that batch. And gamma is a column vector of length 32. And when you multiply gamma by x, you're basically multiplying that column vector gamma by element by every column in the, you're multiplying every column in the matrix by gamma. That's the result.
Gamma 1 is basically multiplied into just image 1, right?
Yes.
Okay.
So you're broadcasting, if you think of it, you're broadcasting a column vector times a matrix, such that the column vector is multiplying each column in the matrix.
Right.
And then beta is a vector of as another column vector of length 32, and then so you're basically adding that, you're broadcasting that added to every column in the matrix, and then you get the new matrix Zi for the batch.
So, but this is just averaging over the batch, and this is 784.
Correct.
So and you're just adding, all the batch, like if it's 64, you're just adding 64 rows and dividing by 64. So where does column come in? This is only row.
Well, yeah, mu b is a row vector, right? And those are intermediate results. Sigma b squared is also a row of length 784.
And where does column come in?
And the columns come in when you look at xi. Xi xi is the batch, is the matrix for the batch.
Right.
Right? And so you're subtracting mu b from it. You're subtracting the mean. In this case, it's another example of broadcasting. Here you've got in equation 3, now you've got x, which is a two-dimensional matrix, and you're subtracting mu from it. Mu is a one-dimensional, is a row vector, right? And so mu b is being subtracted, is being broadcasted onto that. When you do the subtraction, you're basically subtracting that row, mu b row, from every row in X in that matrix X. You're subtracting the mean from each one. And then on the bottom, you've got another row matrix, sigma b squared. Sigma b squared is a row matrix. Forget about the epsilon for a moment. The square root of sigma b squared is also a row matrix. And so now you're doing another broadcasting operation. You're dividing the two-dimensional matrix in the numerator by a row vector, which means you're going to divide it row by row. You're going to divide every row of that matrix by the row vector in the denominator. And then that's going to be a result for the standardized x. So x hat I is another two-dimensional matrix that's 32 by 784.
So only gamma and beta are broadcasted over the columns, I guess.
Yeah. The mu b and the sigma b are broadcasted over rows.
Got it. Okay. So the gamma and beta.
Like image exclusive, for each image you would have those, whereas your mu b and sigma b squared is across images that you're calculating.
Say it again. Say that again.
The sigma square and mu b are things that are calculated across the batch. So if we had like 32 images in a batch, we'd be calculating across the 32 images.
Right.
So there'd be 784 elements in mu b, one for each pixel. You're going to get a mean for each pixel. And you're also going to get a standard deviation. Sigma b squared is a variance for each pixel, 784 values. It's a row vector.
Whereas gamma and beta are exclusive for each image in those 32, images.
For features across 784 features, that's what you're saying.
Yeah, okay, yeah, that's right, yeah.
Yeah.
To be more precise, yes, for each feature rather than.
Yes, okay, that makes sense now. Okay, great. Okay, so then then if we move the first BN layer before the flattened layer, meaning we're not flattening it, then the input batches will be 3D with shape, batch size, height, width. Therefore, the BN layer will compute 28 means and 28 standard deviations, one per column of pixels, computed across all instances in the batch and across all rows in the column. And it will normalize all pixels in a given column using the same mean and standard deviation. There will also be just 28 scale parameters and 28 shift parameters. If instead you will want to treat each of the 784 pixels independently, then you should set x equals to 1, 2. So can someone explain this a little better? Why 28 means and 28 standard deviation, one per column of pixels, and so on and so forth.
So now instead of taking a mean over each pixel, you're taking a mean over each column of pixels. So there's 28, and so instead of having 784 values, you're going to get, because there are 28 columns, you're going to get 28. So it's kind of like the average contains more stuff. You're only going to get 20, and so it's a way of decreasing the number of parameters you have to deal with, right? Yeah. So I mean, if you consider each pixel as a feature, then you're going to need, I guess it's still not changing the number of parameters that get fitted. There's still two parameters per batch that have to get fitted, the gamma and the alpha, the gamma and the beta, but the means get calculated differently. Instead of each pixel getting its own mean, each column gets its own mean. So there's only 28 of them instead of 784 of them.
in the 784 case, you've actually flattened a 2D matrix of 28 rows by 28 columns. Flattened is 1 row by 784 pixels. Instead, if you have a 2D matrix of 28 rows and 28 columns, then you continue to do what you did for the flattened 1 by 784, which is compute per feature, which means per column. So here, per column, when you have 28 rows and 28 columns, is only for the 28 columns. So you now have 28 means and 28 standard deviations instead of 784, or sorry, in this case, just 28 means and 28 standard deviations.
That is basically the default setting when Chang, because access is equal to -1 by default. So that's why if you look at the thing, it's batch size, height by width, and width is 20. Width is just 28. So that's why it's only operating on that one. That's why the last sentence says that if you want to swap that over and make it back into that 784 independent pixels, then you basically say, okay, flatten out height and width. And how do you do that? Instead of that, you basically specify access is equal to 1, 2, where 0 is basically taken off on the batch size. So it's calculated across those, right?
Yeah, yeah. And so each of this main is basically one column's main, right?
Yeah.
And got it. Okay.
So the numbers that go into that calculation are they're going to be 32 examples times 28 parameters in that column. So that's it's 32 times 28 things are being added together and averaged.
Averaged across 38 batch?
32, sorry, 32 batches. And
32.
yeah, and you can imagine that each batch has associated with it a column of 28. And so there's 32 times 28 things that are being averaged together in each of those columns.
Over 32.
Right?
Yeah, over 32. Got it. Okay, cool. So and that's pretty much it. You know, we then he just basically said you can do the call function, you know, to perform the computation, things like that. But I guess you normally wouldn't do that. You just, you know, just call it, you know, by laying out like that. So, okay, well, I mean, this discussion is great, but we're a little short on time now. So let's quickly start reading from grading clipping, and you know, we'll see how far we can get. But ideally, I do want to kind of read it till page 359, right before learning rate scheduling, and let's just go as fast, you know, as far as possible. But if we don't get to finish, and most likely we will not, and that's fine, because we do have 4 sessions, and so that's fine. And let's spend next 40 minutes. So we'll read till like 8 p.m. PST, and then we'll regroup at that time.
Great.
And yeah, and MASH will take over from there. Okay. I think it's time. And Mash, why don't you start?
Sounds good. And if everyone is ready, I shared the notebook that we can use, the same notebook that we used the last session. And so let's go through the next few pages rather quickly, which to me feels a lot like let's be very clever in how we design neural networks based on experience. So continuing on from exactly where Wencheng left off, gradient clipping is another way of dealing with the exploding gradients and vanishing gradients issue that we had started this chapter with that interesting graph, the sigmoid activation function, where we had these saturation points at both ends, the vanishing and exploding gradients. One clever way that they came up with for trying to resolve that was simply gradient clipping. And all that means is just clipping the values as part for the optimizer. Either you can pick a certain clip around a certain value, or you can take the clip norm, which is you can either clip between -1 to 1, or you can clip around based on the gradient vector is this, based on by clipping by the norm of the gradient vector. And so he doesn't go into a tremendous amount of detail, but he does say, here are things that you can do, play around with it, see if it helps. Any questions on that one? Okay, let's move on to a very interesting idea that we build up to, which is transfer learning. Now, transfer learning, let's go through a little bit of a discussion. This was, well, in previous times, can you guys hear me? Just a quick sound check.
Yes, we can.
All right, great, thank you. So in previous times, as they start to build, and I guess this is in the days of old when computational resources were at quite a premium, rather than rebuilding everything from scratch, they would reuse. Even to this day, for a lot of very sophisticated models such as NLP models and so on, we pre-train certain segments and then we retrain only other pieces to it. I'm not a great expert on some of these ideas, beyond just knowing that that's how they work. If anyone has specific experience with how this is done, please jump in. The process being where you train up to a certain point, then you freeze it, and then you train differently with different weights.
Yeah, I can jump in really quick. I mean, just by referencing FastAI, basically what FastAI does is it freezes, unfreezes the last two layers. And within a CNN structure, convolutional neural network structure, and it only trains the last two layers. And the reason being, and also Jahan mentioned it, the last two layers kind of capture the high level features instead of the low level features, which mean high level features meaning like it's more detailed, graphic features rather than structures and edges, which would be captured at earlier layers, and those are called, I guess, low level features. And then once you do that, once you fine tune the last two layers, then you unfreeze all the previous layers, then you train it again, and then you're done with your training process. So
yep. And so we begin to see exactly that idea implemented when we get with transfer learning. And so I'm sure all of you have already walked through read through this section. Let's walk through it in code. We're going to use the fashion MNIST data set, where we're going to take two different splits of it for creating a model A and a model B. So for model A, we'll take the entire fashion MNIST minus sandals and shirts, values 5 and 6. And we'll keep that and use that to train model A. Do the usual train validation split for A. But for B, we'll take sandals and shirts that we had held out, but only the first 200. So we're not using all of it. And the purpose of it is, let's go ahead and build a training model for everything but for model A with everything but sandals and shirts. So here we go. You go ahead and build that specific model, and you ultimately get down to one that has an accuracy of, at least for me when I ran it, 92.62. His value was a bit different. Save that model, .h5 file. Now let's build model B, and recall model B is the first 200 sandals and shirts. Run that, go through this, and you get to a model that is very, very accurate. So save. Now that we've got model A and model B separately, we, of course, an interesting little tidbit, if you were to use model A and start to try to sequence and sort of weave in with model B, just as in Python, you have a symbolic copy and a deep copy, same idea, at least to me, that you don't just work with model A with model B, and because when you do, you've now impacted model A. What you really want to do is make a clone of model A, so you don't really ruin the original model A. And then on that, you tack on model B with a different set of weights. Put it together, compile it together, and you rebuild your model. Now, you recall the accuracy of model A. Let's run this again. This time we've spliced in model B into model A and get its evaluation metrics, and voila, what we see is that we've dropped the error rate by a factor of 4. Now, this is an interesting, clever trick. He, of course, goes into an interesting explanation. So, yeah, great. This may look very, very convincing, but please be aware, I cheated. He trained that model together, and he chose different parameters and all of that after working very, very hard, as he put it. I'm sure all of us have heard this term before, torturing the data to death until it confesses, or torturing the data until it confesses. And so making also the point that you never want to trust a particular model that is if it's too good to be true, then it probably is. And goes on and on to explain a little bit more about the background there. Any questions? I'm going to stop for a moment, take any questions up to this point, or any thoughts.
So we kind of saw batch norm layers before this, and I think point of discussion is if he was showing something where you can fuse a batch norm layer, and from my understanding is if you end up fusing a batch norm layer, then doing something like this where you're trying to do transfer learning, I'm guessing that would not work because those batch norm parameters are now no more like independent. They've kind of been fused into the convolutional layers weights. So I was just wondering if that is right or anyone has thoughts. I've usually used fusing only during, like, finally when you're deploying stuff so that you have lesser number of weights.
Yep.
Any other point of contention on that? Like, can you still do transfer learning if you even end up fusing?
Or fusing with data sets where, in this case, the images came from a similar-ish set, right?
You're not fusing the data sets, right?
Right.
When I say fuse, I was talking about the batch norm.
Right, referring to the model, and the model is built on the underlying data set.
Right.
And so you're fusing models, and even if the data set is different, it's still the idea that you're fusing different models. And to me, maybe I don't get the math as intuitively, but to me, it seems to, it just doesn't quite feel intuitive yet, I guess. Rekil, I wondered if you felt the same way.
All right, so that's what I personally think that you cannot. So that's why I was just wondering if someone else has any other insight as to whether that is right or wrong, or does that make sense? Because I think when Joseph was going through the activation functions also, that's kind of the tricky thing. When you use a pre-trained network, you can't go back and swap a relu out for a mesh or anything like that. The same thing happens, like even you can't go back and swap out a batch norm for a group norm or something like that. You basically can't change anything from your previous network when you're trying to do transfer learning. And I think that same thing would apply for fusing a batch norm layer, but I'm still not kind of completely convinced. If I'm missing something.
Rekil, sorry, could you define what you're saying by, or what you're using the term fusing to mean exactly?
So we just looked at fuse batch norms, right? So basically you have a separate batch norm layer, which would give you 2 parameters, gammas and betas, and a bunch of, for your batch size. So now when Wenchang went through, he showed us that equation that where you would take your output from your last layer, subtract the mean, variance, divide by variance, all that, but then you multiply that into that gamma and that beta during training. But when you're kind of deploying, at that point of time, you already know what your gamma and beta is. So you don't have to keep those parameters separate. You can multiply them back into your previous layer's weights. So then you're saving on those batch norm parameters. So your model weights would kind of reduce. Now the question is, can you use that same model, which has lesser number of parameters because of the fusing of batch norm, for transfer learning?
Yeah, but, so you're saying the alternative would be that you do not do the fusing, right? You retain the
Correct, exactly.
So that's the alternative to the fusing approach.
Right. Other words, you basically should use fusing. I think you should use fusing only when you're like finally going to deploy, and like you're not going to be using that for like.
Yeah, not even during transfer learning.
Exactly.
It's after the transfer learning that you can collapse the batch norms.
Yep.
But when you are still transfer learning, then you don't fuse until it's
but you
done.
cannot
That's
transfer
what you
learn if you've already fused. Like if model A in this example was already fused, where the batch norms were already gone, you cannot use model A for transfer learning. Is what
exactly. Yeah,
right?
that's that. Yeah, yes, right. Because then you don't have that batch norm values. It's embedded in your weights.
Right. Yeah. Okay.
Would it have mattered that model A had the final layer activation function being a softmax, and model B had a model final activation layer being sigmoid? And if you look at what was fused, they chose sigmoid. Now you're fusing B on A.
I think Mash, you and I are using fuse in completely different terms. When I'm saying fuse, I'm talking of batch norm fuse layers, which is just taking the batch norm weights and literally multiplying them with the weights of the previous layer. When you're talking of transfer learning, this is just appending. You're basically literally copying off the weights from another model, detaching the head, and then throwing on a new head there with some more layers, and then retraining that.
Right.
So for this, yeah, this, yes, I think, yeah, that kind of makes sense. Like what Shreya was also saying.
Yeah.
Yeah, I think that's the fact that you were using fusing for batch norm fusing of the two parameters into the weights versus what Mash you were focused on was that's the thing I was pointing out, that what Rekil was saying was when he was using the term fusing, he was referring to what in the book the guy tells you that it's simpler to do, and then he goes on to transfer learning without, I think what Rekil is highlighting, and it's an important point, is without pointing out that you can't fuse and then do transfer learning using batch norm. He probably doesn't do that, but it's an important point to highlight for people learning that, because you would assume that, oh, wait, I'm reducing the weight, so let me just fuse. And then I go on to transfer learning. As Rekil points out, that won't work. You need to keep it separate. And then, won't work meaning, you make it, again, as with many things he points out, you might get lucky, but it's not, quote, the proper way to do it.
Yeah.
Yeah, like we already know that you can't do it like by changing activation or like any of the norms. So I was just kind of
right. Yeah.
wondering if it kind of holds with this also. I think it does.
So fusing is something that you do, Rekil. So fusing is something that you do right before the prediction part of the model, right? So
yeah, I would imagine literally just before deployment, when you want to like condense your model weights to a smaller size and something like that, you would end up doing that.
So what it means is you are just using the earlier calculated mean, standard deviation, gamma and all. Is that what it means?
Not really. Otherwise, what would have happened is you would have run, let us say, your image through a CNN first filter, right? You would have run it through your first filter, you would have got an output. Now this output, let us say we go with the activation first. So we passed it through a ReLU. So everything is between 0 and some max value. Now you would use your batch norm values that you have already calculated for gamma and beta, right? And so now you're doing 3 sets of operations. When you say fusing, what would happen is this gamma and beta that you're doing in the third step, that literally goes multiplied, let's say, into your weights. So then instead of doing 3 sets of operations, you end up doing just 2 sets of operations.
Yeah. Mm-hmm.
So that is what I understand what fusing is. And so that's why I'm saying, like, I think those 2 parameters can no more be trained now because they've kind of been multiplied in there. So you can never use it, I would imagine, for like transfer learning scenario. This is something that, yeah, I don't know. This is the question that I'm asking, and I'm wondering if it makes sense to people here, or is there some point of contention on that? Does that make sense, Gautam?
Yes, yes.
Okay.
Yeah, the concern makes sense for me intuitively as well, and I just don't get it yet. I wish there was some way, if there was additional material that we could dig into a little further.
I guess we could just perform the experiment and, like, yeah, fuse it and then try transfer. Yeah, just need to do with that.
Yeah. I'm presenting live, so I won't do this. But I was curious if I would, if I were to copy the code and make some changes in the parameter and experiment around a little bit. All right, moving on, because I want to help. I want to get us to optimizers really quickly. He does go from that interesting point to this notion of unsupervised pre-training, and he'll be describing that a little bit more later in future chapters around autoencoders and GANs. But he does describe this specific part of the architecture that was used by Jeffrey Hinton and his co-authors. You guys can read through this. And again, this kind of points to what Rekil just described and mentioned. That's it, without going into all the details. Wenchang, do you want to pick it up from there? Because we're right.
That's fine. Yeah, I think it's 11:21 p.m. Or 8:21 PST. It's probably fine to leave this entire section till next time, but because we do have 2 more sessions to go, so we have enough time for this chapter, and we can go through the optimizers next session. And I want to go, because there's not much code in the notebook, and I do want to go through the Jeremy Howard's Excel workbook. As I've gone through it previously, it's quite helpful to kind of go through that, and I kind of add a bunch of plots with how gradients behave during each epoch in the Excel. So it's helpful to visualize that with the simple linear regression. But I think before we wrap up, I just want to kind of show how this was done for the people who have not gone through FastAI in terms of transfer learning, because I do feel like this is great potential, and it's fairly easy from a FastAI implementation. So yeah, so this is FastAI notebook, literally lesson 1, and it's already going through basically using ResNet as a pre-trained model, and you're just passing the a parameter called models.resnet, and then pass into a CNN learner, and metrics equals to error rates. And when you call that learn.model, it'll go through every single layer structure with all the parameters, kernel size, strides. Similarly, you can do that with model.summary with Keras, as we already did. Okay, so then you do learn.fit one cycle, and fit one cycle is basically kind of it incorporates learning rate annealing, which we'll talk about learning rate scheduling later on in this chapter, but Oh, where did it unfreeze? I'm sorry, 1 second. Oh, then after like it trained once, right? Here for 4 epochs, then it did some EDAs. But then he unfroze the some of the layers, and usually it's the last 2 layers, and you just call learn.unfreeze. And he was saying basically, since our model is working as we expect it to, we will unfreeze our model and train some more. So you first only fine-tune the last couple layers. You know, you want to check your error rate is fine, it's dropping, you know, consistently, and it's conversion already, and then you unfreeze, then you train a little more, meaning you're now training all the parameters across all layers. Then you do a lr.find, recorded.plot. Then you try to basically find the loss that basically it kind of, you know, you want the learning rate range that is at the steepest loss. Then you kind of feed that into that. Then you train a little more after you unfreeze. So
does this notebook run currently, Wenshang? Because I think you have 2 learn.unfreezes, and the second learn.unfreeze doesn't seem to be.
Yeah, I don't know why he added this, and this was straight from the course v3. So this was not my notebook. This was from the official GitHub. Yeah, I don't know why he unfroze twice. Yeah, but you guys get the gist of what's going on here. And this is how FastAI does the transfer learning. And for computer vision, it's models .resnet 34 of 50. And I believe for NLP, he also did one for transfer learning. Let me just find out right away. It should be this one. Yep. So, and yes. So, and here you passed in AWD LSTM. That's the Wikitext 103 pre-trained model. Then, you know, then you can do transfer learning on NLP. So yeah, and it's the same, roughly same thing. You know, you do fit 1 cycle, then you unfreeze, then you train more. And yeah, it's kind of the same drill every time. And FastAI kind of specializes in that, you know, in terms of transfer learning. I think they literally were some of the first people who did transfer learning NLP and had really, really great results. So if you have not gone through that, this is one way of doing transfer learning in a very intuitive and fast way. So, okay, any questions, comments before we wrap this up?
Sounds like we have homework before next class. Go over FastAI Notebook 1.
It's right there.
Just one comment, which kind of took me a while to figure out with terminology, I wanted to share with you guys, was that when you do transfer learning, the side where the image comes in, and you have the side where you get your final output. The side where the image comes in, that side is usually called the body. And the side where the output comes out is called the head. Now the body is even called a feature extractor, and the head is even called as a classifier. Again, the body is again called an encoder. So there's like jargon overload tremendously on this side. And that took me a while to understand. It's kind of unintuitive to understand which side is the head, which side is the body, but that's what the body is towards the image and the head is towards the output. And when even in the current stuff, we were looking at lower features and low features and high features. And low is again towards the body side, and the high is towards the output side.
Same as early layers and later layers.
Early layers and later layers.
Yeah, the early layers are towards the input, and the later layers are towards the output. So you're kind of thinking of a left to right processing in some way.
Right. Or if you basically start, so basically your input image will be the largest, and as you go down the chain, it'll become smaller and smaller. So if you flip that on the image, it'll become like a pyramid. That's the way I kind of remember what the body is and what the head is. The head is at the top of the pyramid and the body is the bottom bar. So if that helps.
Thank you. Thank you. That makes sense. Cool. Anyone else?
Yeah, I just wanted to make a comment that we're very close to halfway through the book. So I just wanted to congratulate everybody who's stayed with the class, and we will make it through this book.
Great. Awesome. Yeah, I mean, everything going forward is neural network and different network structure. Should be very exciting. And cool.
Sharon makes a mention of you should kind of tune your layers with lesser learning rates as you go towards the input. And that's what you get for free from FastAI. Otherwise, you would have to do like layer.trainable is equal to false in like segments. Whereas FastAI automatically kind of divides the model into 3 parts and then would give you like 3 decreasing order learning rates. And if you think about it, it makes sense because the layer closest to the model, either if you're doing cats versus dogs or you're doing buildings versus anything, your edges are still going to be the same. So that layer probably is the least that you want to tweak. The mid layers is probably slightly more than that you would want to tweak. And your classifier or the head of the model is the one which is like pretty much completely changing. So that's the one with the largest learning rate that you would tweak with. So yeah, all that is kind of built in when you call CNN learner. But yeah, it's interesting to see.
Yeah, absolutely. Yeah. Cool. And the momentum is the reverse, right?
Yes, and that kind of makes sense, right? If you look at fit one cycle that you were showing, a triangle, it's actually a triangle, right? And the momentum corresponding to that would be an inverted triangle. And the reasoning is I think it's pretty intuitive, is that as your learning rate is increasing, that means at a higher learning rate, you're going to be taking bigger jumps. Now, when you're taking bigger jumps, you want to start trusting the momentum, right? You want to be more careful. Basically, momentum is all it's saying is that give me I trust more of what has happened before than the current value. That's why it's like 0.99 of the previous value and then just 0.01 of the present value. So that's why they're kind of inverted to each other. And then when your learning rate becomes smaller, that means, okay, you're taking smaller steps. So then now you can say that, okay, yeah, the higher the momentum, I can go like in a more rapidly in that direction sort of thing. So that's why they kind of balance each other out like that.
Yeah, absolutely. Okay.